Without memory, every single conversation will start from absolute zero. The agent has no idea what you discussed 5 minutes ago, let alone last week. This creates a frustrating experience because users naturally expect continuity. Human conversations build on prior context and shared understanding, and when an agent can't do that, it feels broken. So, what does having memory actually enable in practice? First, agents can remember user preferences, past decisions, and critically the reasoning behind those decisions across multiple sessions. This means if a user told the agent 3 weeks ago that they prefer concise responses, the agent should be able to remember that without being told again. Second is that the complex multi step tasks become achievable with memory. The agent can maintain state and track progress towards goals over extended time frames. Think about having a research assistant helping with the month long project. Without memory, that would be pretty impossible. The third is that error correction actually improves because the agent can now recall what failed before and avoid making the same mistakes again. This is how genuine learning happens. Now, here's the cost of getting memory wrong. Too little memory, and your agent will feel frustratingly forgetful. Users will lose trust quickly when they have to repeat themselves constantly to the agent, but too much memory without proper management creates a different failure mode. The agent gets confused, retrieves irrelevant context, and performance degrades significantly. The key insight is that the right memory architecture should balance retention, relevance, and retrieval speed for your specific use case. There is no universal answer here, and that's what makes this topic so important to understand deeply. Let's talk about short term working memory and how it actually functions in agentic systems. The context window is essentially your agent's working memory. This is where active reasoning happens and where the agent has immediate access to recent information. Everything currently in the context window competes for attention and for your token budget, which means careful curation directly determines the quality of reasoning you'll get. Here's the key principle: working memory should contain only what's immediately relevant to the current task, plus whatever essential background context is needed. Anything else is noise that can actually hurt the performance. So, how do we manage the context windows effectively? The first strategy is rolling summarization. As the conversation progresses, older messages get compressed into summaries while recent messages stays in their original form. This preserves the full detail of what just happened while maintaining awareness of earlier context. The second strategy involves hierarchical importance scoring. So you will need a system to decide what stays in full detail versus what gets summarized or removed entirely. Not all information is equally important, and your memory system needs to reflect that. The third strategy is budget allocation. You should reserve dedicated token budgets for different types of content. System instructions need their own allocation, user context needs its own allocation as well. Conversation history and retrieved knowledge each needs their own space too. This prevents any single category from crowding out the others. Now, for technical implementation, there are a few considerations that matter. You should track token counts continuously and trigger summarization before you actually hit the limits, rather than truncating arbitrarily when you run out of space. You should be storing full conversation history externally so summarized content can be retrieved if the conversation circles back to an earlier topic. And consider using smaller, faster models specifically for summarization tasks. This reduces latency and cost while still preserving context quality. Now let's talk about long-term memory architecture and how vector databases fit into the picture. Vector databases store embedded representations of past interactions, documents, and learned information. The key capability here is semantic retrieval. Embeddings capture meaning rather than exact words, so the agent can find relevant information even when the user phrases things differently than before. This enables retrieval augmented generation where relevant long-term context memory get pulled into the context window exactly when they're needed for the current task. The agent doesn't have to remember everything at once, it just needs to know how to find what it needs. Now, when you're designing your memory schema for scale, there are a few important decisions to make. First, you should separate memories by type. Conversation history is different from user facts, which is different from procedural knowledge, which is also different from external documents. Each type has different access patterns and different retention requirements. Second, you should be including rich metadata with every memory entry. Timestamps, they do matter for recency, confidence scores matters for reliability, source attribution matters for verification, access patterns matter for optimization. This metadata becomes critical when you need to filter or rank retrieval results. Third, you should be planning your indexing strategy based on expected query patterns. Retrieval speed matters enormously for real-time interactions. A user waiting 3 seconds for the agent to find relevant memories is a user losing patience. Then there's chunking, which is one of the most important decisions you'll make. Semantic chunking splits the text at natural boundaries like paragraphs or topic changes rather than fixed character counts. This preserves meaning much better than arbitrary splits. You should also implement overlap between chunks. This ensures that information at boundaries does not get lost retrieved during the retrieval. You should be adding chunk size should match your embedding model's optimal input length while also considering your retrieval precision requirements. In my experience, chunks between 300 and 800 tokens tend to work well for most use cases, though this depends heavily on your specific content and query patterns. Now let's talk about episodic memory and why it's a distinct and valuable memory type. Episodic memory captures specific events and interactions as discrete retrieval episodes. The key difference from other memory types is that the temporal context gets preserved here. Each episode includes what happened, when it happened, and who was involved, and what the outcome or resolution of the interaction. This matters because it allows the agents to reason about sequence of events. The agent can learn from specific past experiences rather than just general patterns. When a similar situation arises, the agent can recall exactly how a previous similar situation played out. So, how do we structure episodes for effective retrieval? First, store episodes with clear boundaries. Make the start and end of each coherent interaction on task completion. Without clear boundaries, you end up with the fragmented memories that are hard to retrieve meaningfully. Second, you should be including outcome tags indicating whether the episode was successful, failed, or partially completed. And you should also be including specific details about what made it successful or why it failed. This outcome information becomes valuable when the agent needs to decide how to approach a new situation. Third, you should be linking related episodes together. This allows the agent to retrieve entire conversation threads or project histories when relevant rather than isolated fragments that lack context. Now, here's how learning from past episodes actually works. When facing a new situation, the agent retrieves similar past episodes to inform its current approach. If the agent successfully helped the user debug a similar issue last month, that episode provides a template for the current situation. You should also track which retrieved episodes actually helped versus which were irrelevant. This feedback loop improves the retrieval quality over time, and you should also be constrained to add the episode outcomes to build procedural knowledge about what works and what doesn't in specific context. Over time, patterns will emerge from individual episodes, and those patterns will become reusable knowledge. Now, let's talk about semantic memory and how to build a knowledge base your agent can actually use effectively. Semantic memory stores facts, concepts, and relationships as structured knowledge. This is different from raw conversation log. The goal is to extract and store user preferences, stated facts, and learned information in normalized formats that will support reliable retrieval. A critical component here is maintaining confidence scores and source attribution. The agent needs to know how certain it should be about each piece of knowledge. A fact stated directly by the user deserves higher confidence than something inferred from context. Entity extraction and relationship mapping form the foundation of semantic memory. You should automatically extract named entities like people, organizations, projects, and dates from conversations as they happen. You should build relationship graphs connecting entities so the agent understands how different pieces of information relate to each other. Then, when new facts do emerge, you should update the entity information accordingly and critically handle contradictions thoughtfully. Don't simply override the old information. Instead, you should track recency and confidence levels to determine which version is most likely correct. Keeping semantic memory current and accurate requires active maintenance. You should be implementing decay functions that reduce confidence in old information that has not been recently confirmed or assessed. If the agent learned something 6 months ago and it's never come up since, the information should be treated with appropriate skepticism. You should also be creating explicit mechanisms for users to correct wrong information and ensure those corrections propagate through related memories. If a user corrects the agent about their job title, any memories that reference the old job title should be updated. And regularly validate stored facts against the new information as well. You should be flagging potential contradictions for review or clarification rather than silently maintaining the inconsistent knowledge. The goal here is to maintain a memory system that stays accurate over time, not one that actually accumulates errors. Let's talk about procedural memory, which stores how to do things rather than just what happened. Procedural memory captures learned skills, successful workflows, and effective approaches as reusable templates. When the agent successfully completes a complex task, you can extract that approach as a procedure for future similar situations. The key distinction from episodic memory is generalization. Episodic memory stores specific events. Procedural memory stores patterns that transfer across contexts. If the agent helped 3 different users to set up authentication, the procedural memory captures the general approach that worked, not the details of each individual interaction. Building and refining procedures over time involves several steps. Start with the explicit procedures from documentation or user instruction. These will give you a baseline. then you should be refining those procedures based on actual execution results. What the documentation says should work and what actually works in practice can often actually differ. You should track success rates for each procedure and identify which steps commonly fail or require user intervention. These hire actually procedure where it needs improvement and allow procedures to have variants for different contexts. A procedure for setting up authentication might have variants for different authentication providers, and retrieval should select the most appropriate variant for the current situation. For procedure retrieval and execution, match incoming tasks to stored procedures using semantic similarity and explicit task classification. Sometimes the user's request clearly matches the known procedures. Other times you will need a semantic matching to find relevant procedures. Retrieve relevant procedures into the context and allow the agent to adapt them to a specific current situation. Procedures are templates, not rigid scripts. And after each execution, update the procedure metadata with the outcome information. For example, did this procedure work? Did the user need to make corrections? This feedback will improve the future retrieval and selection, creating a continuous improvement loop. Let's talk about retrieval strategies and how to make them work at scale. Pure vector similarity search often retrieves results that seem plausible, but they aren't actually useful. Semantic similarity doesn't equal usefulness. Two pieces of text can be semantically similar while one is relevant to the user's actual need and the other could be totally irrelevant. So we need to go beyond simple semantic search. You should be combining semantic search with metadata filtering to narrow results by time range, memory type, or confidence threshold. This dramatically improves the precision. You should be using hybrid retrieval that combines dense vector search with sparse keyword matching. Vector search will find semantically related content. Keyword search will catch exact matches like specific names, codes, or identifiers that vector search might miss. Re-ranking retrieved results adds another layer of relevance filtering. So initial retrieval should cast a wide net, pulling back more candidates that you will ultimately use. Then a re-ranking model scores each input for actual relevance to the current query. Cross-encoder re-rankers are more accurate than bi-encoders for their final ranking step, but they're also slower. So use them on candidate sets after initial retrieval, not on your entire memory store. Also consider the current conversation context when re-ranking. Relevance depends on what the user is actually trying to accomplish right now. Handling retrieval at scale requires additional techniques. Implement tiered retrieval where fast approximate search narrows candidates before expensive, precise re-ranking. This will keep latency manageable even with millions of memories. You should be also caching frequently, access memories, and common query results. If users often ask similar questions, you should not be running full retrieval every time. Also, monitor the retrieval quality metrics continuously. Track whether retrieved memories actually get used and whether users seem satisfied with the results. Retrain embedding models as your training distribution actually evolves because embeddings that worked well initially may become less effective as your memory store grows and changes. Let's talk about memory consolidation and lifecycle management, which are pretty important for long running memory systems. Without active management, memory systems accumulate noise, outdated information, and contradictory facts over time. Performance degrades gradually, and eventually the system becomes more hindrance than help. Consolidation processes should regularly review stored memories to merge duplicates, resolve conflicts, and remove obsolete entries. Think of this like human sleep, where the memories actually get reorganized, strengthened, or forgotten based on their importance and recency. Your agent's memory system needs similar processes. Implementing effective forgetting mechanisms is counterintuitive but pretty important. Not all information deserves permanent storage. Active forgetting prevents retrieval degradation from irrelevant results crowding out the useful ones. You should be using access patterns to identify memories that are never retrieved. If a memory has not been accessed in, let's say, 6 months and nothing else references it, that's a strong signal it can be archived or deleted. Implement tiered storage where hot memories stay in fast retrieval systems and cold memories move to cheap archive storage. You can always promote cold memories back to hot storage if they become relevant again. Conflict resolution deserves special attention here. When new information contradicts existing memories, don't simply overwrite. The old information might actually be correct, so implement explicit conflict detection that flag contradiction for resolution through user clarification or confidence comparison. You should be maintaining version history for important facts so you can trace how the agent's understanding evolved over time. If a user later says the agent used to know something correctly and now it's wrong, you need to be able to investigate what changed and when. This audit trail will become invaluable for debugging and for building the user trust. Let's talk about the production implementation patterns and how to bring everything together. Starting with architecture decisions that matter most, separate your memory service from agentic logic. This separation lets you scale, update, and debug each component independently. Memory systems and agent reasoning have different scaling characteristics and different failure modes. Design memory APIs with clear contracts for write, read, update, and delete operations. You should be including proper error handling for cases like failed retrievals or storage limits, and plan for multi tenancy from the start. Retrofitting user isolation into a shared memory system after the fact is extremely difficult and error prone. You should be building it right from the beginning. Latency optimization matters enormously for real time agents. Memory retrieval often dominates agent response latency, so optimize retrieval paths before spending time optimizing the generation. You should be implementing speculative retrieval that starts fetching likely needed memories while the user is still typing. And you should be using streaming responses that begin generating while memory retrieval completes in parallel. This hides latency from users even when the retrieval takes time. Monitoring and debugging capabilities determine whether you can actually maintain the system in production. You should be logging every memory write and retrieve through enough context to debug why the agent remembered or forgot something specific. You should be also tracking retrieval quality metrics, including the precision and various result counts, meaning the reciprocal rank and the user feedback on the retrieval results. You should be also building tools to inspect what the agent remembers about specific users or topics. You will absolutely need this for debugging when something goes wrong, and something always goes wrong eventually. Now, let me summarize what we have covered. Working memory in the context window handles active reasoning, while long term stores handle persistence and scale. Episodic memory captures specific events. Semantic memory captures facts and relationships. Procedural memory captures learn, skill, and workflows. And effective retrieval combines vector search, metadata filtering, and re-ranking to surface the right memories at the right time. For implementation priorities, start with the conversation history persistence and basic semantic retrieval before building sophisticated memory types. Add user fact extraction and preference learning once basic retrieval works reliably in production. Then add implementation consolidation forgetting mechanisms only after you have enough data to understand your actual memory patterns. These techniques form the foundation for building agents that genuinely learn and improve over time. For more implementation and code examples, please feel free to provide me feedback. And thank you for watching today. Have a good day. Bye.